Okay, so one of the problems that we recognize with Miller compensation is that though we do get the desired result in terms of our poles, it introduces a right half plane zero. And as we just learned, the right half plane zero causes problems because it increases the negative phase shift while decreasing the roll-off and the gain. And so one thing that we might think of as a solution to this problem is to stop the feed forward, which is what causes the zero. So how might we do that? Well, one, we could add a buffer. So imagine that we have our compensation capacitance and we put an ideal voltage buffer in the reverse direction. Our ideal voltage buffer has a gain of 1. So this is our output now and our input from the perspective of the compensation. So what happens here is if it's an ideal buffer, our forward current won't propagate. But the reverse current will. Okay, so looking at our simple circuit model for our op-amp, we got our input coming in here. We had a voltage dependent current source, big GM1 times Vn. We have the output resistance of the first stage, R1, and of course some capacitance from that first stage, C1. We develop a voltage across C1, which we'll call V1. We have the second stage, which has a voltage dependent current source, GM2 times V1. And of course the output resistance and capacitance from that second stage, R2 and C2 respectively. And we take our output from the second stage, V out. And we might have a load capacitance tied to the output as well. So with this buffering compensation, we imagine placing our compensation capacitor with the buffer going from our output back towards our input. Our buffer has a gain of 1 and our compensation capacitor is here. Now if we do KCl at the input and output nodes, we would find a couple of things change. First, we would find a pole frequency, a dominant pole frequency, omega P1, is equal to 1 over big GM2 times R1 times R2 times CC. Well, that's exactly the same as it was in the first case, and so that's not a problem. Our second pole omega P2 would still be approximately equal to GM2 over the load capacitance, CL. But we would get a third pole in this analysis, and our third pole, omega P3, would approximately equal 1 over the output resistance of the amplifier times C1, where the output resistance would be found by placing a test voltage source at the output and measuring the current that flows through it. Now, we still have a 0 in this case, but the 0, omega Z1, is approximately equal to 1 over the output resistance times the compensation capacitance. But this new 0 is a left half plane 0. And so this one doesn't cause a negative phase shift, instead it causes a positive phase shift, so it doesn't add to the phase shift problem that we were having before. One of the problems that we'll find is, how do we actually add this buffer? But if we summarize what this buffer did, it added a pole, omega P3, but the pole is probably at very high frequency, so it probably does not affect our stability problems. And it also added a left half plane 0, and the left half plane 0 helps our stability because it adds a positive phase shift rather than a negative phase shift. But again, what we're going to find is that adding this buffer is problematic. And we will look at that in a moment.